So yesterday, we talked about how to describe our quantitative displays. So if we have a bar graph, a dot plot, or a stem plot, not a bar graph, a histogram, a stem plot, or a dot plot. So what three things do we absolutely have to make sure we mention when we are describing or when we're analyzing? What are the three pieces we definitely have to make sure we mention? Shape. So that's the first thing, shape. Then we can measure our center, and then the spread, okay? Now yesterday we really just touched on the basics for those. So shape is really as basic as that. It's either symmetric or it's skewed left or right. There's really not much more to that part. But center and spread become a little more complicated depending on what shape we choose. So yesterday with center and spread, we really only touched on median and we touched on range. So median was a measure of center, range a measure of spread. Today we'll get a little bit more into center, so talking mean versus median, and then we'll talk about another measure of spread, which is called the IQR. And then tomorrow we'll actually talk about how the IQR can be used to create another graphical display, and then we'll talk about our last measure of spread, standard deviation, on Friday. So we're going to kind of do it in parts and kind of build on these ideas. So, first thing, the median. Yesterday we talked about the fact that the median is simply the midpoint of the data. So if you arrange your values from smallest to largest, you find the exact middle value, or find the middle values and average them, you have found your median. So we're looking for that piece that has 50% of the data above, 50% below. The median, a little more information on that, is what we call a resistant measure. This is an extremely important vocab term. You absolutely need to know what it means to be resistant versus non-resistant, because that's a huge portion of deciding what type of measure of center or what type of spread that you want to utilize for a given graph, for a given distribution. So you have to know what it means to be resistant. When we say a measure is resistant, it means it is not influenced by outliers or skewed data. So if we think about a list of values, let's say, okay, so 4, 5, 6, 7, 8, that's our set of data. What's our median? 6, okay? So median would be at 6. But let's say I accidentally recorded this last value wrong. Instead of 8, it's supposed to be 20. So now here, our values were all pretty tightly clustered, probably no outliers within the data. But we said, okay, well, I accidentally did that one wrong. It was actually supposed to be 20. Now, what's happening here? What would we consider 20 to be? An outlier. It's something that doesn't follow what the rest of the pattern looks like. We have everything at 4, 5, 6, and 7, and then all of a sudden it jumps all the way to 20, right? But what's our median? 6. It didn't change at all, right? We could do that with a low outlier as well. We could have said instead of 4, it's supposed to be like -5, okay? So it's not going to change what the median is. When we say something's resistant, if there are outliers or if there's skewed data, this is key here. If there is skewed data, the median is completely unaffected by that. It will not change because of those values. It's still the midpoint regardless of what you have going on. Okay? So median is resistant. It will not change because of outliers. Right? So that's the first thing, which means if you have a skewed set of data, you have a skewed distribution. So you've examined the distribution, you've decided it's skewed right or it's skewed left, your measure of center has to be the median. So we talked yesterday, when you start describing, you start with shape. Shape will determine center. So if it's skewed, median is your choice for center. The other thing you want to look for are outliers. The data might be symmetric, but it has a really high outlier or maybe a really low outlier. If that's the case, you want to use the median for your measure of center because that outlier is going to affect mean, which we'll talk about here in a little bit. So median is not affected when the data is skewed or when there are outliers. So that's your choice once you determine that's the shape of your graph or your distribution. All right? Mean, on the other hand. The mean, you all know as the average, right? If I give you a list of 10 values and said find the mean, you would take those 10 values and do what? Add them all up and divide by 10, right? So you add up your 10 values, divide by 10, there's your average. That's what the mean is. Now what that means then is that when we calculate mean, we are accounting for every single value in our set. Median doesn't care what the individual values are. It could care less what each of the individual values in our set are, it just wants to know where the midpoint is. The mean actually takes into account what those individual values are, which is why it is so greatly affected by outliers and skewed data. Because it knows when something's a lot larger than it should be or something smaller than it should be, and it pulls in that direction. Okay? Now as far as calculating, you know how to calculate, but one of the things that might be pertinent for you is knowing some notation. Because like I said, for most of your tests and quizzes, you'll get this formula packet. That's the same packet that you'll get on your AP exam. Well, in the AP test or in the AP packet, they don't just say mean is add the numbers and divide by the value or number of observations. They'll give you notation. So you need to know that the mean is denoted as X bar. So X with a little line segment symbol above it. So we pronounce that X bar in statistics, and they're going to use a notation similar to this. Instead of saying add up all the values, they're going to say use this sigma notation. You guys know what sigma means? You've seen that before? Okay. When you see this little sigma symbol, it means add up all of your X values. So whatever values are in your list, add them all up, and then divide by m. This really actually means sum. So when you see the sigma symbol, it just says sum. So add those values up, divide by the total number of observations. N is going to be a pretty generic letter that we use for the number of observations, the number of individuals in a set. Okay? So you're looking for this formula when you want to calculate mean. Alright? Like we just kind of discussed a little bit ago, mean is not resistant. So median didn't care if you had really high or really low values, didn't care if your data was skewed. Mean does care. If we have a really high outlier, the mean is going to get pulled towards that high outlier. That one value can take our overall average and jump it up quite a bit. If we have a low outlier, your mean is going to be pulled towards that low outlier. The same thing happens with skewed distributions. If we look at a distribution, I'm just going to draw kind of a smooth curve to it. Okay, so imagine we have a histogram with bars that follow kind of this smooth pattern here. So if we look, the left side versus the right side, this would be skewed right. The tail falls off to the right. Now our median would fall somewhere fairly close to our big peak. We're trying to find that 50-50 point, right? So our median is going to fall somewhere right in here. But the mean, which does account for every single value in the set, what's going to happen is, yes, it's going to account for these smaller values, but it's going to notice that there are lots of big values that taper off towards the end. These big values way up here, are going to pull the mean in that direction. So when you're looking at a set of data, if you know it's skewed to the right, the mean will be larger than the median. That might be something you want to write down, because some of the questions that you'll be asked, whether in homework, quizzes, tests, it's going to say, here's a distribution, here's two measures of center. Which one is most likely the mean? Which one's most likely the median? So if it's skewed right, the mean is going to be larger. It's getting pulled towards those large values, whereas the median can stay pretty centralized because it doesn't care what those values are. What do you suppose would happen if we were skewed left then? The exact opposite. The median would be larger than the mean, because the mean is going to get pulled towards those low values in that skewed left distribution. What do you suppose would happen if the distribution was symmetric? They're going to be the exact same. They should both fall directly in the middle, right? So they're going to be very close together, if not the exact same value. So if your distribution is symmetric, they're both going to be right there. What happens if you have a distribution? And again, I'm just going to draw kind of a smooth curve to it. And treat that dot as if it was another value outside. So we've got the boxes, or the bars, that fill this smooth curve, and then we have an observation way up above here. Where's the median going to be? If I asked you to place a line where the median was going to be, where would you probably put it, roughly? Yeah, pretty close to the peak, right? So basically, right on the peak is going to be our median. Where would the mean go? Towards the outlier, right? So if the median is sitting right at the peak, like we would like it to be, the median is going to be pulled, or the mean, sorry, is going to be pulled towards that outlier. So outliers pull the mean in that direction. So mean is a non-resistant measure. If you have outliers in the data, you do not want to use your mean as your measure of center, because it's not going to be as accurate as it could be. It's going to be influenced by those outliers. Or if you've decided your distribution is skewed, you do not want to use mean, because that mean is going to get pulled towards the skew. Does that all make sense? All right. So calculating mean. Now here's one where, if you're doing it by hand, it really just involves adding up all the values, dividing by the total number, right? So if we wanted to calculate mean, here's what it would look like. Add up all the values, divide by 20 in this case, because we have 20 randomly selected New York workers, we get our mean, so 31.25 minutes. Okay? Now in your calculators, I want to talk about this now. If you get your calculators out, so if you have your calculator with you, get it out here real quick. I'm going to show you how to do this on the calculator so you don't have to sit here and add up all the values and divide and all that stuff every time. Plus, it'll lead into kind of some of the stuff we're going to do tomorrow. So your calculator will calculate mean for you. The way to do that, and this is going to be pretty standard, every time you want to have your calculator do something for you statistically, you're going to want to edit your list. There's going to be lists that you can put data values into, and it'll do stuff for whatever you want it to do with those lists. So what you need to hit is, you need to look for the stat key. So stat key should be pretty much right by the number, or the arrows, right? So hit the stat key. Now on the first screen that comes up, it says like edit, calc, tests across the top. We want to edit. We're going to input information right now. So hit enter on the edit, and it should take you to a screen where it just gives you lists. So it should say like list 1, list 2, list 3 across the top, right? And then a bunch of blanks down below. So pretty much any time you want to enter information into your calculator, that's where you go. Stat, enter. So now in list 1, list 1's generally going to be the one we're going to use, so we'll stick to 1 and 2 because it makes things a lot easier. So in list 1, go ahead and place these values. So just hit 10, enter, then 30, enter, and so on. Get those 20 values entered into your list there.
KJ, I don't know exactly. I think you go about the same side. And then I'll just hold each side and I'll do this one. So that's
All right. So everybody got that? So the next thing, once you have your list entered, now as soon as you enter those values in, your calculator is automatically saving those values. So even if you hit second quit right now, it's going to save everything you had put in there automatically. So it's always going to be there until you go in and physically delete that stuff out. So once you have your list entered, you're going to hit the stat key again. That's where you're going to find pretty much everything we're going to do with those lists. Now this time, we already have our information entered, so we don't need to edit our list. Now we want to actually calculate something. So we're going to scroll right to the Calculate tab. And now what you should see is like 1 var stats, 2 var stats, like option 4 is like linreg ax plus b, stuff like that. Everybody see that screen? So what you want is 1 variable stats. We have 1 list of values that we want to analyze. So you're going to hit enter on the 1 var stats, and then just enter again. So some of you might get a menu that comes up. It says like what list do you want to use, keep it at list 1. Don't do anything with frequency or whatever else pops up, and just hit calculate or enter or whatever. And so right off the bat, you get this whole screen full of information, right? What's the very first thing it gives you? X bar. X bar is our mean, okay? So your mean should be 31.25, just like we calculated up here, right? All right. So if you want to calculate mean, and you don't want to sit there and add up every single value from a list of values, you can just type them in real quick in the list, hit 1 var stats, hit enter, it's going to give you mean. Now this process will also give you standard deviation, which we'll talk about on Friday. It'll also give you what we call the 5-number summary, which we'll talk about tomorrow. So this is going to be an important step that you're going to want to utilize multiple times to get this information, okay? But right now we're just talking mean. Now, what we can notice here, if we look at this actual distribution, so here I just created a stem plot of this set of data. What do we notice about the shape of our distribution? It is skewed. Now, on stem plots, this is what's kind of tough to figure out, like the skewed right, skewed left nature. If you ordered from lowest on top to largest on bottom, to figure out whether you're skewed right or left, imagine that you're just laying it down to the left side. So on your piece of paper, if you just shifted it, like just laid it down on its left, what would we notice? What direction would that go? It'd be skewed right, okay? Or I guess you could just tilt your head to the right and look at it sideways, right? So it's going to be skewed right. And what else do you notice is happening in there? Outliers. There's at least one outlier way up at 85, right? So would mean be our best choice for center? No, because it's going to be pulled towards that skew and towards those outliers there. So if we notice, we kind of highlighted here, if we look for our median, these two values constitute the middle of our data. So if we average those, our median is only about 22.5 minutes. Notice the large difference. That is almost 9 full minutes difference for one unit of, or one measure of center. So when you are describing or using, trying to decide which set or measure of center to look at, shape is going to be important because it can drastically alter your results. And what happens is people can use those different results to kind of trick you into believing something that's not true. If they wanted to, for some reason, show that New Yorkers have a larger than average commute time, they're going to report the larger of the two values, even though it's not the correct one to use. Right? So people can use that difference to kind of mislead you into believing something that's not technically true. So that's another thing you have to always be aware of when analyzing results. We okay with that? All right. So, using the mean really only makes sense when we have a symmetric distribution. So if the distribution is symmetric, there are no outliers present, we want to use the mean. As far as mean versus median, the mean is actually a stronger measure because it actually does take into account every single value. The problem is when we try to use it with outliers or skewed data, it gets tricked by those large or small values. That's why we don't use it except for when we're symmetric. If we're symmetric, the mean is going to be the one we want to use because it's a much stronger measure. If the distribution is skewed or has outliers, the mean doesn't work as well. Like I said, it gets kind of tricked by those different values, so the median is what's going to be used instead. So now, when you describe distributions, once you've established the shape, I'm going to expect that you choose the correct measure of center. So shape is going to determine which measure you use. So if you say it's skewed, but you report the mean, that's going to be wrong. If you say it's symmetric and you give me the median, I'm going to count off for that. When it's symmetric, use your mean. When it's skewed or has outliers, use the median. And that's going to be something that you have to explain your choice in some of the problems. So why did you choose mean versus median and so on? So do we understand the difference between that? All right. Spread. Like I said, we're also going to introduce one more unit, or one more measure of spread. We're going to talk about the IQR. So, like we just got done discussing, a measure of center, if we use it alone, can be very misleading. So if all we do is try to describe an entire distribution with one single number, we can often be misled as to what the overall distribution really looks like. So yesterday we mentioned, whenever we choose a measure of center, we have to make sure we also report a measure of spread. We have to know how the data spreads around that particular center point. So, a measure of spread, or the spread combined with the center, will give us the most complete picture of what this distribution really looks like. So center and spread together are going to be the keys here. So, the measure of spread that we're going to discuss right now is called the IQR. IQR stands for interquartile range. So the first thing, we need to calculate what are called the quartiles. Have you heard that term before? Nobody? What's the median? If I asked you to define the median, what would you say? The exact middle number, right? It's going to cut the list in half. The quartiles, so if you've defined a list of values and you've defined a median, that median has cut into two separate sets, one below, one above, right? The quartiles are like the medians of those two sets. So it's going to cut the bottom half in half and cut the upper half in half. So when we talk about quartiles, we're going to essentially follow the same steps we did for finding median. We're going to start by arranging our list in ascending order, and we're going to locate the median. That's the first thing, is we have to cut our list in half. Once we know where the halfway point is, now we know that 50% of our observations are left, 50% are right. So what we need to do then is find the medians of those two lists separately. So the first quartile is called quartile 1, or you'll see it listed as Q sub 1. That's the median of the observations located left of the median. So that's the median of the lower values. So first quartile, or quartile 1, is the median of your lower 50%. The third quartile, quartile 3, is the median for the observations located to the right. So that's the median of your upper values. So when you're asked to calculate quartiles, arrange your list in order, find the median to cut your list in half, and then find the median of each of those halves separately. So the lower half will give you quartile 1, upper half will give you quartile 3. Now we go from quartile 1 to quartile 3. Where's quartile 2? The median. Since we have a specific name for that, we don't ever call it quartile 2. It's just always the median. All right? So those are the quartiles. It's basically cutting your distribution into fourths. So quartile 1 is 25% larger than any of the other values. Median is 50% larger. Quartile 3 is 75% larger. And then you have your maximum, which is 100% larger than any other values. So just kind of cutting it up into fourths. Okay? So once we know what our quartiles equal, so once we know what quartile 1 and quartile 3 are, we can calculate our IQR. So here's the formula to calculate IQR. Again, interquartile range. Most of the time you guys see range and you think interval. Range is not an interval. It's a specific number. It's a difference. So if we talk range by itself, range is max minus min. It's the difference between the largest and smallest value. Interquartile range is the range of the quartiles. What's the difference between the larger quartile and the smaller quartile? So Q3 minus Q1. And we're going to talk about examples where we find these by hand, but that process I showed you guys on finding mean, that will find your quartiles as well. And we'll talk more about that tomorrow when we get to that point. So we can find the quartiles in the calculator again without having to reorder everything, find the median of each side, and go from there. So I show you by hand, but most of the time you're just going to use your calculator to find all this stuff. So if we go back to our travel times for New Yorkers, we have our 20 values. First step would be to split them into, or rearrange it, put it in ascending order. Then we'd go through and find our median. So our median would happen at 22.5. So we find the two middle values, since we have an even number, average them. Then, when we go to split, so since we were here, we're going to use these new values to find our new middle, which would be between the two 15s here. If we average those, we get 15 since it's the same value. Same thing over here on the right side of our median. We're going to follow in until we find the middle. So between 40 and 45, average it, you get 42.5. Okay with that so far? Now, if I ask for the IQR, what would I need to do at this point, now that I have my quartiles and median? Very good. Take your 42.5 minus your 15. Here's your interquartile range. So if I were reporting my analysis, if I were describing my distribution, remember the stem plot showed us that it was skewed right with outliers. We would choose our center to be the median. That would be the measure we'd want to use. So our median is 22.5. Our measure of spread then could be the IQR. So we calculate our IQR. Our spread that we report would be 27.5 minutes. So we'd say the IQR is 27.5. If you wanted to interpret that, what the IQR really gives you is the middle 50% of your data. So here is where the middle 50% of all my observations lie. So the range of the middle half of travel times is 27.5 minutes. So 50% of all of our observations fall within a 27.5-minute window. Does that make sense? So when you think IQR, think middle 50%. That's the key. All right, now, the importance of the IQR. I said yesterday, when we look at distributions, there are times where we see values that fall outside the normal pattern. We see these outliers. Well, yesterday, we were kind of using outlier pretty loosely. We were simply saying, hey, this point doesn't follow, it's an outlier. Let's examine it. But we have a very specific way to determine if values are in fact outliers or not. So they might be unusual, they might not follow the pattern exactly, but they might not be far enough away from the pattern that we actually consider them to be an outlier. We don't consider them to have that big of an effect on our non-resistant measures. So we use what's called the 1.5 IQR rule. If a point is more than 1.5 IQRs above quartile 3, so our starting point for the upper half, if we start at quartile 3 and we add 1.5 times our IQR, that's going to give us a value. So depending on the data set, it's going to give us something. If I have any values in my set that are larger than that, they're outliers. Or I can check lower values. If I take my quartile 1 value and subtract 1.5 times the IQR. So if I reach 1.5 IQRs in each direction for my quartiles, I'm giving myself a range of values that are acceptable. If I'm within 1.5 IQRs of quartile 3 and I'm within 1.5 IQRs of quartile 1, I'm an acceptable value. If I get outside of that range, I'm no longer acceptable. I'm an outlier that needs to be examined or eliminated from the set, depending on what you're trying to accomplish. So this is going to be the way we determine whether items are outliers or not. So now, when you say something's an outlier, you have to be very clear that you have checked this 1.5 IQR rule and have shown it to actually be an outlier. So here, if we go back to our 20 New York travel times, we said our IQR was 27.5 minutes. So if I wanted to check, if I wanted to see maybe the 5 we think might be an outlier, or we said probably the 85 because I was way off to the top, right? So maybe that's an outlier. Now we can actually check definitively. So what we would need to do is calculate what we call the upper and lower fence. The upper fence tells us the maximum value we allow before it's considered an outlier. The lower fence tells us the lowest value we accept before it's an outlier. So if I want the upper fence, and this will need to be done every time you want to establish outliers. If you want to calculate the upper fence, you're going to take quartile 3. You always start at your quartiles. One of the things people always tend to do is use median as their starting point. When you calculate your upper and lower fence, use your quartiles. Okay? Make sure you write that down, highlight it, whatever you need to do in your mind to keep that straight. It's always quartile. So quartile 3, 42.5, plus 1.5 times our 27.5. So that's just quartile 3 plus 1.5 times the IQR. So what that's telling us is our upper fence is 83.75. If I have a value less than 83.75, it's perfectly acceptable. So if I look at my data set again, do I have any outliers? Yes, we do. In this case now, we can definitely say which one's an outlier. 85. Now notice that in that stem plot, if you kind of think back to that, there was a gap. So we have this 40 and 45 area here. Then there was a gap with the 60s and the 65. And we thought, well, gaps probably mean outliers. But that's not always the case. So if you see a histogram or a stem plot that has gaps in it, you cannot automatically assume that those values are outliers. Because if we notice here, 60s and 65 are perfectly fine. They're well within our upper fence, our allowed values. So don't assume gaps automatically mean outliers. They have to be far enough away to be considered that. And that's a definitive cutoff, that upper fence. When we do the lower fence, it's the exact same process. The only difference is now we start at quartile 1. So lower starts with the lower quartile. So 15 minus 1.5 times 27.5. So our lower fence would be negative 26.25. So if I had any values smaller than negative 26.25, they would be considered outliers. Do we have that issue in our distribution? No. So on this side, our minimum value is still considered okay. There are no outliers on the lower end, but there's one outlier on the upper end. Does that make sense? Okay. So here's your assignment. Now, one of the things I suggest, you need to memorize that upper fence and lower fence formula. Those are going to be huge. And they are not formulas that are given to you in the packet for your quizzes and tests. So those are two formulas you have to know on your own. You have to know you're using the quartiles. You need to know that you're doing 1.5 times the IQR when you add and subtract. You have to know those. And we'll get more practice with that tomorrow, because tomorrow we're going to talk about what's called the 5-number summary and box plots. And it's all going to require those upper and lower fences, calculating median IQR, things like that.